So we spent a lot of time hammering in the octet rule. However, the octet rule is at least partially a lie because there are a few instances where we don't obey it. We already know of one instance for hydrogen, which has a duet rather than an octet, but in this video we're going to learn about some more. Let's start with phosphate, or PO4 3-. Knowing the rules about Lewis structures, pause the video and write out the structure for phosphate now. Be sure to calculate all of the formal charges and write them next to each atom. So hopefully you came up with this molecule. Phosphorus is in the center because it has the largest bonding capacity and also because it is the least electronegative atom. The phosphorus has a single bond to each oxygen. Everyone's octet is complete, but each oxygen has a negative charge and the phosphate has a positive charge. It's true their charges are small in magnitude, and the positive charge is resting on the least electronegative atom, while the negative charges are resting on the more electronegative atoms. But if your spidey sense is going off that something's wrong, well, you're right. It's generally a bad idea to have a non-zero formal charge on every atom in a molecule. So what do we do when we know we want to make some formal charges go away? We move around electrons. Specifically, we move some bonds around or even take lone pair electrons and make them into bonds. We know that oxygen has a charge of -1 because it has 1 bond and 6 lone pair electrons when it started with 6 valence electrons. So how do we get oxygen from -1 to 0? We take one of its lone pairs and make it into a double bond with the central atom. But wait, we can't do that. If we were to take one of oxygen's lone pairs and turn it into a double bond, that would make phosphorus have 5 bonds, and we've seen atoms have more bonds than their bond capacity allows, but we haven't yet seen a central atom that exceeds 8 valence electrons. But it turns out that phosphorus can make 5 bonds and exceed the octet rule. And this is what that structure will look like. For phosphate, the structure has 1 oxygen with making a double bond to the P, and the other 3 oxygens have a single bond. If you don't believe this works, then do the formal charge calculations for all of the atoms again. Yup, you guessed it. The formal charges for the double bonded oxygen and the phosphorus are now 0 instead of -1 and +1. So this is a situation where we break the octet but minimalize the formal charges in doing so, and in this case, the formal charges win out. Even if you go through and do the math, we still have a net charge of -3. Now, since there are 3 other oxygens, we have 3 additional resonance structures that contribute to the actual structure of phosphate. Is one of these 4 equivalent resonance structures favored? No, but we can definitively say that the resonance structure for which the phosphorus is singly bonded to each oxygen is not the favored structure or the major contributor. So let's think back to a resonance structure that we talked about the last time, carbonate. We noticed how carbonate had 3 equivalent structures, all of which had one of the 3 oxygens doubly bound to the carbon. And we came to the conclusion that all 3 of those structures were equivalent, and so the resonance structure, the actual structure of the 3 molecules was really an average of the 3, or a blending, and so the result is that the actual structure of carbonate didn't have 1 double bond and 2 single bonds at any given point in time. There was actually about 1 1/3 bonds per atom, per carbon oxygen at any given point in time. This is a similar thing with phosphate. If we were to draw what the actual structure of phosphate would look like, we could pick one of those equivalent resonance structures, or we could represent it like this. Either way, we know that the actual bond length for the phosphorus oxygen bond in phosphate would be somewhere between a single and a double bond, but probably closer to a single bond. That's all fine, well and good, but you want to know when it's okay to break the octet rule. Because we don't just break the octet rule willy-nilly, we break it for the common good aka to minimize the formal charges in a molecule. But this can only happen under certain circumstances. The first circumstance is that Z is greater than 12, or we have an N greater than or equal to 3, and we're in the P block. Why this? Because once you're in the third period and you're over on the upside of the periodic table or over in those P elements, when you have an N greater than 3 or equal to 3, this means you have access to d orbitals that can accept the extra electrons. So atoms like phosphorus, sulfur, because these atoms are in N equals 3, they're able to shunt some extra electrons to make an expanded octet by accommodating them in the 3d orbital. So elements that have a Z greater or N greater or equal to 3 or a Z greater than or equal to 12 have the ability to expand their octet due to the availability of d orbitals. But we're not only going to see atoms expanding their octet when it results in formal charges being minimized, and we'll only see this happen if the formal charge is minimized and electrons will only be added to the octet of the central atom until the formal charge of a central atom reaches 0. The next exception to this rule is when we have odd-numbered electron molecules. So let's take NO for instance, or nitrous oxide. It has a total of 11 electrons, which is an odd number. When we draw out the skeleton number of NO, we can put a single bond between them, add valence electrons, but there's still going to be an extra electron. Even when we take one pair to make a double bond, we still have that pesky lone electron. It's okay, it happens. And if we have an odd number electron species, unfortunately, we are not going to have a complete octet for each atom. Now, if your spidey senses were going on that this molecule would have a resonance structure, you're absolutely right. We have two options. We can put the single electron on either element. Which structure is favored? Let's do the formal charges. When the lone electron is on the nitrogen, both nitrogen and oxygen have a formal charge of 0. When we move the lone electron to oxygen, however, oxygen has a charge of -1 and nitrogen has a charge of +1. Although both structures contribute to the molecule structure, the one that will be the best representative of the molecule structure, or the major resonance contributor, will be the one where the formal charge is minimized. So that will be the first structure where we have the lone electron on the nitrogen. Finally, our last exception is atoms that have less than an octet. This can happen to elements in group 13, so boron, aluminum, etc., and groups 1 and 2. This is because these atoms only have 1 to 3 valence electrons and therefore can't make the 4 bonds needed to satisfy an octet. For example, let's take BF3, or boron trifluoride. We have 5 and 21 to give us 26 electrons. But if we draw out our skeleton structure, complete the octets for each fluorine, we have the desired amount of valence electrons, and all of our atoms have formal charges of 0. Actually, boron, that's 3, so that would give us 24. So it's 3, 21, and 24. So if we were to go, we have 8, 16, 24. We have 24 valence electrons, and that checks out. Now, normally, this electron would show us a red flag because our central atom does not have a complete octet. However, boron, since it only has 3 valence electrons to start with, boron can have an incomplete octet, so this would be the correct structure, as all of our atoms would have formal charges of 0. The same is true for group 1 and 2 elements. So, if you see a group 1, 2, or 13 element in a Lewis structure, remember that with these, like hydrogen, which has a duet, you won't get a complete octet.